Okay, let's get started. So our last speaker also a Frontier Science Award winner, Dr. Siyuan Chen, now at Shanghai Astronomical Observatory, a researcher at Shanghai Astronomical Observatory, and also used to be a Kafley Fellow at Kafley Institute, PKU, a member of KJ's group. So Siyuan is a member or has been a member of the executive committee of the European Pulsar Timing Array and also collaborating with the large European array for pulsars and also the North American Nanohertz Observatory for gravitational waves, NANOGrav, as well as the International Pulsar Timing Array, IPTA. So today, Siyuan is going to tell us about the NANOGrav 15-year data set gravitational wave result. Please go ahead.
Yep. Yeah, thank you very much for the introduction. And since I forgot to give a speech or record a message at the ceremony, I think I'll do it now. So on behalf of NANOGrav, I'd like to thank the ICBS and the selection committee for giving us this FSA award. It's nice that our work in the little Pulsar Timing Array community is recognized by a larger group of people. And we're hoping that in the future we have more achievements together with our IPTA colleagues to share with the broader community. So with that said, I will start my talk. I know this is the last talk of this afternoon and of this week, so I hope I will not spend too much time. I don't have that many slides, but I hope the share will stop me if I talk too long. Okay, so these are the four figures you've seen like a lot of times now by now. These are the main results we published last year and for which we've received the awards. Ian Jun talked yesterday about the EPTA results. Andrew talked about the PPTA results, and Xu Heng, on behalf of KJ Lee, talked about the CPTA results. So what's left is just the NANOGrav one, and so I'll do that. And NANOGrav is a big collaboration. Well, we're not as big as LIGO also, but we are sort of a medium-sized collaboration. There's about 50 or so institutions with 100 plus people at it, and here are just some example institution logos. Of course, we're not just institutions, we're also people. This is from the spring meeting 2023 at Oregon State University. So there are some members of NANOGrav that went to that meeting. And if you have so many people, you have to somehow organize things. And so this is sort of an organization chart. I know this is boring. So the main thing is that the main sort of body that governs NANOGrav is management team. The elected chairs, so and members, so things go by election in the collaboration. And then because we are funded by the NSF through the Physics Frontier Center, we also have the co-directors. And then there are various sort of external committees across that. I just want to use this just to point out the sort of working groups here, and that's also how the sort of individual science goals that NANOGrav has is sort of selected, right? Of course, there are also supporting working groups like EPO and CyberEye, so these are supporting types, but the main ones are sort of searching, timing, noise budget, gravitational wave detection, astrophysics, and new physics, which is the new group that came to be with NANOGrav. Right, so I want to spend maybe 2 minutes to summarize PTAs because you've heard a lot, but still just to summarize. How Pulsar Timing Array works is we need pulsars, so we need objects that are very stable and emit regular radio photons over a very long time period. And so you can time those and over decades, and you can use a model to predict when you should receive each of the parts of the pulsar. And this is the sort of timing model. And so if you have that model, you can use it to compare against your observations. So I predicted arrival time now, and I compared. If there are small deviations, these are the residues. And so having these residues, this is where sort of the signals that are not part of your timing model comes into play, right? There are things that we call red noise. So this is the sort of overall noise that each individual pulsar has during the time that it rotates. And so that you have to add as well. And if you go look at one pulsar only, and you look at the photons that travel, they have to travel through interstellar medium. And so that is not a static thing, right? It varies over time. And so we need to sort of measure that as well and model that. And in our jargon term, this is the dispersion measure variation. And then the photons keep traveling, and so they pass through some gravitational waves, either like a field of a background of gravitational waves, or maybe it's some individual source that's just nearby and happens to affect the travel time of the photon. And then they go through the solar system, which we have heard that we need to accurately model the ephemeris in order to account for all the effects that the photons meet during the travel. And then finally, we need a radio telescope, which is an instrument on Earth, to actually detect and measure the photons. So when they are observed at a telescope, it will automatically introduce some white noise just from the instrument, because any measurement that you do has some white noise, right? And then the other part is you need these sort of clocks. So in order to be able to compare what you measure against some time standard, you need to have a clock at the observatory, and you need to compare the signal that you get at the observatory time against the sort of global time, right? And so this is where your clock instrument is important. And if there's some sort of problem with your clock, that impacts all the observations that you do, because it's used to compare all your TOAs. And so if you look at one pulsar, you have this many effects that can happen from the emission to the propagation and to the detection of these radio waves. And so what we do is we look at many pulsars in order to separate terms that are intrinsic to one pulsar, like red noise, or the interstellar medium in this direction is different from another direction, and the gravitational wave, right, which is common. So if it's a background of gravitational waves throughout the local universe, then that's stochastically common across all the different pulsars you observe. And so this is where the sort of Anderson-Downs correlation comes from. You look at two different pulsars, and if there's a stochastic background, the amount of correlation depends only on the angular separation of the pulsar. And this is what we do in the IPTA. Oops, that's the wrong direction. In the IPTA, and also NANOGrav. So NANOGrav we have used for telescopes. Now it's free. This one is a green bank telescope. Then we have the Arecibo telescope, the VLA, the Very Large Array in New Mexico, and then the Chen, Canadian Hydrogen Intensity Mapping Experiment in Canada. So traditionally, these upper two have been sort of the main two instruments that were used for all the past NANOGrav data sets. And this VLA was added recently. And in the future, we're hoping to also add observations from Chen. The visualization of the dataset is here, given by Thankful Chromaty. So this is time as it goes from early observation to now. And then this axis is just the number of pulsars. Putting names will not make any extra information. And so each box represents each of the NANOGrav data sets. So from the 5-year, 9-year, 11-year, 12-year, 12.5-year, and 15-year data sets. So you can sort of see that the increase in each point is one observation. You can see the increase in number of pulsars and time as it progresses. And there's a big jump from 15-year data set compared to the last one. And if you notice these gaps here, this is because of some instrumental issue at Arecibo. And we have so NANOGrav philosophy not to observe too many pulsars with both telescopes. I think only 1713 and 1909 are observed with both telescopes, and all the other ones are just observed with one telescope. So if you have some issue there, then you basically get a failure. And I think there were several months which observations were taken, but no one actually realized that there was some issue until later on. And so we had to throw away all the data for that period. Oh, I do not need this. Yeah. And so the 15-year data set consists of 68 pulsars. There's nearly 16 years observations. It's 15.9. We decided on 15-year. Between 2004 and 2020. The radio frequency range is between 300 to 4,000 megahertz. The cadence is roughly monthly. It's the first data set to have VLA observations, and it's also the last data set to have Arecibo because it collapsed in 2020. Actually, no, it's not. Anyways, it should be the last one that has data from Arecibo. Yeah, and example of a pulsar is here, 1909, for example. On the different sort of panels is the DMX value. So this is the value of the measured DM variation over time. So the changes of the interstellar medium between us and the pulsar as you sort of measure it over time. You can see sort of a trend here. So you have to model this into your model. I think this is the sort of whitened noise. So when you remove all the noise modeling, you get these residuals, and this is the one with without noise modeling, and these are different types of these type of figures. And on the right, there's some measurement of a Shapiro delay, which gives you information on the secondary if the pulse is not binary, and you can that has an effect on the propagation of the radio photons when the binary sort of orbits. Then when the photon passes through the binary, that sort of gives a delay on the arrival times. And using that effect, you can try to sort of constrain the mass of the companion. And these are sort of the measurements that we get compared to the 12.5-year data set compared to the 15-year data set. And we can see that the blue ones are usually, I mean, they're consistent with most of them, and they're usually a bit better constraints compared to the orange ones. And there are also new values that are like these three pulses that are new. So after you have the observed data, you need to model that as with the noise, and that's what also described in the previous talks. This is a schematic on the process again. So again, you have the interstellar medium effects here, and then as the photons propagate through space, depending on the frequency that they have, they are more or less affected by the interstellar medium. Right? So if the frequency is higher, which means they have a higher energy, then they are less likely to be scattered or scattered by the electrons in the way. And so that's why you can see sort of this drift here at high frequency. It's like Anyway. And so anyway, if you correct for this effect, you can stack them, and they seem all on top of each other again. And again, you have a receiver and clock, and this gives you the final TOA output. Right, so we analyze all the pulsars, looking for the red noise in them, and this is a sort of representative figure here, where this is frequency, and then this is a quantity of the amount of signal or noise in that given pulsar. The orange ones are sort of in each of these points here, sort of frequency independent measure. So you try to measure that frequency. What's the amount of variation that you get for that pulsar? And the orange ones are that you get for the noise modeling. And you can see that, if you try to fit some power law through those, it sort of fits with most of these points, right? Except maybe the first one. And then this blue area is when you take into account a power law, and you try to see if there's sort of extra noise at a particular frequency that your power law does not fit. And so if that happens, then that would show up as some extra noise that you would need. And these are just the base factors to tell you whether there's any frequency which your power law is not modeling well. And for most pulsars that we checked, we didn't find any sort of significant evidence that you would need some extra term to describe the noise more than a power law. Now, once you have, this is what we use for the paper, but you can go further, right? You can try to use non-power law models, and you can try to do things more advanced. This is work that's ongoing, but here's our 6 pulsars were chosen. I think they were chosen to compare against other PTAs, and there's different details, but there's different points, there's different colored contours is just different types of noise modeling that you apply to the pulsar. And you can see that however you model it, has an impact on like what your recovered red noise amplitude and spectral index is for this particular pulsar. And by extension, they will also have an impact on the gravitational waves that you measure. And there are things we know and we have not necessarily included in the models. So things are like solar winds or events in certain pulsars. And so these we can include in the models to try to optimize them. But I will go and there's more things you can check. So we all have the sort of same analysis software package, right, that we use for the analysis, the Bayesian inference and the frequency analysis. So we wanted to check those and make sure that they produce unbiased results. So this is sort of the analysis pipeline check. So we went through the code, and the aim was to just find any bugs if there was any bugs. See if you can improve performance as you have more TOAs, more pulsars, your computation slows down. And in general, just we review the package. We use pp+ to check that we get results that are unbiased. So pp+ is when you, for example, you have like this, 0.4. So these are sort of simulations. So if you simulate a signal and you then use your pipeline to detect a signal, for example, within 40% of your injected regions, you should find that signal in 40% of the chance, right? And so this is sort of the expectation that you get sort of this one-to-one correlation, and then each of these red lines, I think, is from one simulation or so. So it's one analysis of one simulation, and you can see that they also fall within this line. So there's no good bias in our analysis. The right one is frequency analysis, similar concept, and there's two lines that are shown here. Right? This gray is just the expected of 1, 2, 3 sigma deviation, and there's two lines that are shown here. This blue one, which is sort of an old method that we use to compute some signal to noise, and that seems to have been biased. It's clearly not 1-to-1, right? It's sort of higher up, and then it's flatter, and then so we check that and we try to improve this method. And so the new method that we use is gives this sort of orange line, which is closer to the expectations. And so that was work that was done in order to make sure what we get is sort of unbiased. And so what we get from the actual analysis is this figure here. This is sort of the main figure. This was shown is the Hamilton ounce. This again is the same correlation curve with angle and correlation. This is from the frequency analysis. So you have basically compute as Siyuan has showed for the CPTA. You compute the correlation for each pulsar, and then you sort of average them over over certain bins to get some value, and then you can see if it fits the expectations. The left one is the frequency versus expected delay. So this gives you just the strength of the signal as a function of frequency, and you can fit certain power laws through those, which gives you these contours on the bottom here. The blue one is normalized to 1/1 year, which is somewhere here at the edge actually. So it's an ancient conversion. And the orange ones are normalized to 1/10 years, which is somewhere here, I think. So it's just a normalization issue. And so we look at the expected value for the circular population mass local binaries, which is indicated by this dashed line, is somewhat in tension with what we measure from the data set. And that's also seen in this figure here. So the expected mass local population is this black dashed line, where sort of the median power law that we measure is this blue one. So there's some possible tension there. So this actually doesn't tell you like how significant the detection is, right, compared to this dashed curve. So what we did is to try to get some kind of null distribution, right? So if there was no gravitational signal in the universe, right? What kind of signal to noise or base functions would you get with your analysis, right? And because we have one universe and we can try to simulate universes, But the one way is to do do phase shifting. So you take your data set and you add a random phase to the different pulsars, which means you break the correlation in time that there should be when there's a signal that's common, right? And so you do that, and you do that many times, which means you preserve the properties of the pulsars, but you also try to create a data set that doesn't have a gravitational wave signal, right? And so you do that many times, and you get this sort of function, this curve here, which shows just as an integrated thing, right? So at 1, it's 1 minus that. So the signal to noise, low signal to noise, you don't get any, and then as you go to higher signal to noise, you start to sort of have fewer random simulations that give you this high signal to noise. And so that is the curve that you compare to against the value that you get from the data set. And then you can sort of draw some sigma level, right? Which is here in the steps, it's 3, which is for the base factors, I think. And then on the right is the signal to noise, so that's the frequencies analysis. And so this is where the sort of between 3 to 4 sigma comes from. Right, and there were suggestions of how do you cross-check your results, and so there can many things you can do. So I'll just show a few that we did in the paper. This is the DM and BMX versus DMGP model. So this is the model how you model the interstellar medium variation over time. And so the blue is the DMX, which is the standard one that we used, and then this red is sort of the more advanced version. And so you can see that this, just by changing your model for how the interstellar medium changes over time, you get a very different signal in the amplitude spectral index for gravitational wave background. On the right is checking for different correlations. So this is the orange, the Helming's announced. It has the sort of highest, it's the most peak at some value. And then you have different correlations like a common uncorrelated monopole dipole. And you can see that they are sort of consistent with no amplitude at all. This is just some quantity that tells you there's some signal or not. And so this also shows that it's likely that what we see is a Helming's dance compared to the other correlations. Other tests were included, like these ones on the left is ones where we separate the data set between the Arecibo Observatory only and the GBT observations only, which you see in this orange-yellow contours, and the green contours are for GBT. And then the entire PTA is the blue one. So you can see, that it seems that the signal is mainly dominated by the GBT observations and is consistent with Arecibo. Of course, if you separate the data set, you have fewer pulsars in each of those. So in principle, your constraints are worse, right? So you see that the green and orange are worse than the blue one. But it's still somewhat consistent. So there's some measured signal that you have. And then on the right is sort of a modification. So when you go away from having a normal power law, which is the blue, you modify it as a modified power law. If you want to know details, you can ask me, but you can modify power law to account for possibilities of deviations away from that. And that gives you a slightly different parameter values for the power law. But it's still somewhat consistent with what we've seen with a normal power law. These are sort of the tests that we can do, and further you can go further and see like discreteness of the GRBB, right? It should be a power law, or you model it's a power law, and then you can see if there's any frequency that significantly deviates away from that power law. And so you compare that to the orange is the sort of power law, and then this blue are the individual frequency, the power of each individual frequency, and then there's some fractional difference between the two. And see with some sort of statistical measurement how much deviation you have between this point here. The second one is pretty much consistent with the power that you expect here, and then maybe the third and fourth, what you find is maybe a little bit higher, right? So maybe it's a bit inconsistent with that. Here are just some numbers. You can focus on the sigma ones, which just shows you that most of the frequencies are within 2 sigma or so away from a power law description. So we don't have any good evidence for discreteness. Moving on to individual source search. So I've talked about the background. We can also see if there's any individual source that is significant and stands out. And so this is frequency, and these are base factors. And the different lines compare different models and show like how significant they are at this frequency. The model which is in black is the common uncorrelated red noise plus a continuous wave against common uncorrelated red noise. So if you assume that there's only one individual black hole binary in the universe at some frequency, and then you see and you compare that against the description of noise. And so this is the black, it's sort of overall below base factors of 1 or so, most of the cases. There's this small increase here, but it's a base factor of a few, so it's not actually very significant. And secondly, if you change the correlation to Henderson Downs, so you assume that now the signal is a background signal and not just noise, you will see that the base factors for a continuous wave is not, it's basically absorbed, it's basically 1 again, so it's a sort of covariate between that and the background. And then this is 101 here, and then the higher frequency you have basically a lot of effects of from a binary motion of the pulsars, like this one, which is the 1713 orbital binary period, and so there's some sort of signal there, but it's possible it's just 1713 binary orbit, and then so these sort of higher frequencies are various features that I will not that are unlikely to be gravitational waves. On our sky map, we put the upper limit because we didn't find any gravitational waves, so we put the upper limit there. This is how it looks like. You can see that in each of these red points, red stars indicate one of the pulsars. You can see that we have most pulsars, the upper limit is sort of low. Yes, it's 0.2 or so, 10 to minus 14. And then where we have less pulsars here, we have a higher upper limit, 1.4 times 10 to minus 14. Yep. You can also then go a bit further and search for anisotropy. So if you assume it's a background, right, and you assume that it's made of massive black hole, individual massive black holes, then massive black hole binaries, then it's possible that maybe there's one that's very loud and stands out, and so that will sort of create some kind of anisotropy in the background. And so that was also searchable done by NANOGrav. This is a map on the anisotropy. I guess these values are kind of some values of the level of anisotropy. The main thing is they're not. It looks like there's some sort of a constraint, but it's kind of anisotropy, but it's really not, right? The only thing I can say is that this point here is there's maybe a possibility that there's something there that produces a little bit of anisotropy, but the range here is very small actually. And you can convert it to a spherical harmonic decomposition. So you have this L equal 1, 2, 3, 4, 5, 6 terms. So you have 6 spherical harmonic decomposition, and you can put up upper limits on like how strong these individual components should be. These are sort of these lines here as function of frequencies. They are almost always constant across frequencies, and then you can compare it to like a sort of distribution of real universes where you put massive black hole binaries in, and then you compute the expected amount of anisotropy from those simulations. And so you can see that at certain frequencies they should be sort of we are sort of constraining these populations, and and moving on in the astrophysics, this is the interpretation work that we did on the background. And so the way that we do this is through the scheme here, where you have different components of your astrophysics. For example, you have galaxy merger components, and each of the galaxy mergers will produce a black hole binary merger, right? And so then you put in a black hole binary masses into the galaxies, and then you involve the binary, and so that gives you the of merging black hole binaries. And then you add some, you can use either some libraries where you create a discrete set of simulations from massive black hole binaries, or some kind of semi-analytic model to describe the population. There's some kind of interpreter that's outside, and then you basically take the spectra, the per frequency power of the PTAs, and then you compare that against what you get from your astrophysical model, and this gets your results. And this is shown on the right. This gray and green dotted here are the results from NANOGrav. Again, this is the standard one, and this green one is the one with the more advanced DM modeling. And then this blue and orange ones are different model assumptions for your astrophysical population, and so that gives you also different contours of sort of the possible power law that you would get from population of massive black hole binaries. And the main thing is to point out that, within sort of 1, 2 sigma for different assumptions and the different NANOGrav values, there's this sort of overlapping region here of consistent black hole binary population with the results that we get from PTAs. I guess, do I have much time or do I have less time? I have less time. I'll skip this. Okay. The other one is to do new physics. So this is maybe more relevant for this conference here. So there are different models to predict gravitational waves as a background, for example. And these are just some examples here: inflationary gravitational waves, scalar-induced, phase transitions, various type of cosmic strings, and domain walls. And so in a very long paper, all these sort of models were tested against the PTAs. You can find the paper here. And this is a summary figure that shows which of these sort of sources are more consistent with the detected signal. So, in terms of base structure. So, for example, these first ones here, which are scalar-induced gravitational waves, have a higher base structures compared to sort of these type of stable cosmic strings. And then these sort of other models here have also some possibility of being consistent with the data set. We'll skip this, I think. And the last thing I want to talk about is to do polarization research. So there was a mention of doing tests of gravity with PTAs. And so this is looking for a scalar transverse polarization, so an extra polarization of the gravitational waves. And this is sort of base structure comparison. The main points maybe here on the right is to show that the signal to noise that you get for the Hansen-Downs in blue compared to an alternative polarized gravitational wave is about the same. Right? It's also a bit higher depending on the different methods that you use. So there's no sort of evidence that the signal we see is somehow otherwise polarized than Hansen-Downs. This I will skip. What? Yes. So this is a single component optimal statistic, and this is multi-component optimal statistic. So this optimal statistic is just it's a statistic that's used to compute the signal to noise. And then the single component means you assume that there's only one type of correlation, either Hansen-Downs or ST, for example. And then this multi-component is basically if you assume that there's multiple polarizations or multi correlations. Yeah, I'll skip this. I'll just skip this, the summary, and just go to future. So as mentioned, we are planning to do the IPTA DR3. We'll add the PTA data sets that we'll mention in this talk. We'll add millisecond and chime TOAs. And so hopefully that will give us past the 5 or 6 sigma level. And then the future of our NANOGrav by itself is the next NANOGrav data set. It will be in some years. It will have 20 years observations, and it will also have 75 pulsars. And in the US, we're hopefully that the deep synoptic array, which is an array with 2,000 dishes, which are like 2 meters or so, will be built and will be used to do a lot of pulsar time observations. And on the right is the last IPTA meeting we have with all our international colleagues. So thank you very much. I will take questions.
Maybe I'll have a first question. So where is this?
Yes, this is in Italy, in Sexton. So it's in the Dolomites. It's in the mountains. You can see in the background. Yeah.
So maybe I'll have sorry.
So the NANOGrav has now has 3 telescopes, right? So I'm wondering what advantages can we have if we have many telescopes compared with CPTA now maybe has only one?
Yeah. So with more telescopes, you the VLA, the position of the telescopes are different, right? So if it's further in the south or further in the north, you can observe a different parts of the skies. So you maybe get more access to different pulsars. Secondly, if you have more telescope, you hopefully have also more telescope time, right? So you get to observe more.
Sure.
Whereas with one telescope, you have just the time that you can get with one telescope.
Yes, I'm wondering if the telescopes they have, if we use more than one telescope, the signal, do you maybe that's I'm a newbie in this for this observation. Is it related to some kind of interferometer technique, or it's a different band?
You can do interferometry if you have two telescopes, but you can also just use them as standalone, right? Another option is to observe the same pulsar with both telescopes, and so in principle you should see the sort of same signal, right? And that you can use to diagnose if there's something wrong in one telescope, because the signal that you see in this pulsar, which is the same pulsar as you observe in other telescope, is different somehow. So that's something that we use the IPTA, the IPTA for as well, is to compare different PTA data sets on the same pulsar and see if there's some systematic differences between the different PTA data sets.
Okay. To answer my question, the background, the gravitational wave data isn't this kind of interferometry data by interferometer.
No, interferometry is quite difficult. Okay. So you have to make sure that you observe the same pulsar with the telescope at the same time, right? And you have to make sure that sort of the data that you save is sort of comparable. So it's sort of in some format that you can later on add the two together and correlate them to get the interferometric addition, right? And this is more difficult if the telescopes are further away and built independently as independent telescope. It's difficult that the European Pulsar Timing Array have with LEAP. So they have the 5 telescope and they do interferometric observations. NanoGrav is not done with GPT and any other telescope. Yeah.
Thank you.
Yeah.
Siyuan, you talk about this different models. For example, the base, for example, those domain wall as source of gravitational wave. I wonder how do people do this kind of estimate? So basically, you have to build model for those gravitational sources, right?
Yes.
But when you take into your pulsar timing array data, so that basically being translated into 2 parameters, right? One being the amplitude, the other being the
Yes, a bit.
So how is that done exactly?
Technical model, right? I'm not too familiar with these spatial models, so I used here to just show the cosmic string model, right? So for that you have, for example, one parameter which is the G mu nu, which is the cosmic string tension, right? And so using that in your model, you can predict the sort of energy density of gravitational wave as a function of frequency, right? And this is related. This you can. Okay, we have to go back up. Here. This is related to like these frequencies that we measure, and so this y-axis here is a residual, so it's a quantity in time basically. But you can convert it into characteristic strain, or you can convert it to energy density of gravitational waves, and then you basically use this information here to compare against your model. So you constrain your model on these points here.
So instead of using the conventional curve,
Yeah. So instead of using power law, you directly fit your model predictions against the posteriors here, right? So if your model has more, if you can predict a more shallower step or like some curve, then that fits these points better, then that model will be favored.
Questions? Okay. If not, let's thank Siyuan again for the very nice talk. Thank you.
Thank you.